polymerization reactions. Let us recall the classification of polymers based on the mode of polymerization. We learnt that the two common subcategories in this mode of polymerization are addition polymerization and condensation polymerization. We will now study these two modes in detail. Addition polymerization or chain growth polymerization. In this type of polymerization, molecules of the same or different monomer species add together on a large scale to form polymers. These species are usually unsaturated compounds like alkenes, alkynes, etc. An important point to note is that this mode of polymerization leads to an increase in chain length and hence the name chain growth polymerization. As is the case in most of such reactions, the chain growth reaction can take place through formation of ionic species or free radicals. Free radical mechanism. A variety of unsaturated compounds and their derivatives are polymerized in the presence of free radical generating catalysts. Let us study the formation of polythene from ethene, which is initiated or catalyzed by heating or exposing to light a mixture of ethene with a small amount of benzoyl peroxide initiator. The process consists of three major steps: chain initiation step, chain propagation step, and chain termination step. The process starts with the addition of phenyl free radical formed by the peroxide to the ethene double bond and in turn creating a new and larger free radical. This is the first step in a sequence of repetitively similar steps and is hence called the chain initiation step. The new radical formed reacts with another ethene molecule to form a newer and larger free radical. This process keeps on repeating, with the polymer chain becoming bigger and bigger as more molecules add up. This is how the reaction is carried forward, and hence we call this the chain propagating step. But since all good things must come to an end, the long chain can be terminated in a variety of ways to obtain polythene. This we term as the chain terminating step. Polythene. There are two types of polythene: high-density polythene and low-density polythene. We add the prefix high density because this polymer consists of closely packed linear molecules. It is much tougher, stronger, and harder. And as you have correctly deduced, the close packing of molecules ensures that the polymer is chemically inert. This makes it useful in manufacture of buckets, dustbins, bottles, pipes. On the other hand, low-density polythene has branched chains, hence the intermolecular forces are weak. Hence, it is not as tough or strong as high-density polythene. Low-density polythene, obtained under high pressure of around 1000 to 2000 atmosphere and a temperature of around 350 Kelvin to 570 Kelvin. The presence of small traces of dioxygen or a peroxide initiator is required to start and catalyze the reaction. High-density polythene, which is obtained when polymerization of ethene takes place in a hydrocarbon solvent in the presence of a catalyst such as the Ziegler-Natta catalyst. Other popular polymers formed by the free radical polymerization process that we have just discussed are Teflon and polyacrylonitrile. Condensation polymerization or step growth polymerization. I am sure you recall from our earlier discussion that condensation polymerization involves repeated condensation reactions between bifunctional and trifunctional monomeric units, leading to elimination of various byproduct molecules like water, alcohol, halogen acids, etc. However, it is important to note that each step produces a distinct functionalized species independent of each other. Hence, we give it the name step growth polymerization. The formation of pterylene or dacron from ethylene glycol and terephthalic acid is an example of this type of polymerization. Let's now discuss the polymerization processes involving the functional groups that are known to us: amides, amines, aldehydes, esters, and phenols. Polyamides. Polyamides are polymers with amide linkages and are very useful as synthetic fibers. The most common methods of manufacture of such polymers involve condensation polymerization of diamines with dicarboxylic acids or of amino acids and their lactams. Polyamides are also commonly referred to as nylons, the most popular being nylon 6 and nylon 6,6. Nylon 6 is obtained by heating caprolactam with water at a high temperature. It is used for the manufacture of tire cords, fabrics, and ropes. Nylon 6,6, which is largely employed for use in our textile industries, is prepared by the condensation polymerization of hexamethylenidiamine with adipic acid. Its other uses include manufacture of sheets, brush bristles, etc. Polyesters. Do you recall how we obtain esters in the laboratory? Esters are the sweet-smelling products formed as a result of reaction between an alcohol and a carboxylic acid. Link together several ester molecules and you obtain polyesters. Technically speaking, polyesters are the polycondensation products of dicarboxylic acids and diols. The best-known example of such type of a polymer is pterylene, commonly known as dacron. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid at 420 to 460 Kelvin in the presence of zinc acetate antimony trioxide as catalyst. Dacron is a fiber. As we studied earlier, fibers have a high modulus and high tensile strength. This makes them suitable for use as glass reinforcing materials such as safety helmets. Phenol formaldehyde polymers. The phenol formaldehyde polymers are the oldest commercial synthetic polymers first introduced around 100 years ago. Their actual chemistry is complicated and still not completely understood. However, it is understood that these are obtained by the condensation reaction of phenol with formaldehyde in the presence of either an acid or a base catalyst. The reaction gives O and or P hydroxymethylphenol derivatives, which further react with phenol to form compounds having rings joined to each other through CH2 groups. The main reaction is the production of methylene bridges between aromatic rings. The initial product could be a linear product, Novolac, which is used in paints. Novolac, on heating with formaldehyde, undergoes cross-linking to form irregularly cross-linked resins called bakelite. These cross-linked polymers cannot be melted or dissolved, so their synthesis must be conducted in molds for the actual product. Its common usage is for making handles of utensils, combs, electrical switches, etc. Melamine formaldehyde polymers. Melamine and formaldehyde react to form a resin intermediate. This, on condensation polymerization, gives us the required polymer. The urea and melamine-based materials have much less color and so are useful for decorative applications such as dinner plates and countertop materials. Copolymerization. A copolymer, also known as a heteropolymer, is a polymer derived from two or more monomeric species. Hence, the term copolymerization refers to the methods used to chemically synthesize a copolymer. The unique thing about copolymers is that it is possible to synthesize them not only by chain growth polymerization but by step growth polymerization also. Copolymers are vastly different in properties as compared to homopolymers. The butadiene styrene copolymer is quite tough and is a good substitute for natural rubber. Most widely used polymers. Having discussed so many different types of polymers and their methods of preparation, let us focus our energies in understanding the most widely used of all polymers, rubber. Natural rubber. Rubber is an example of an elastomer-type polymer, where the polymer has the ability to return to its original shape after being stretched or deformed. The rubber polymer is coiled when in the resting state. The elastic properties arise from its ability to stretch the chains apart, but when the tension is released, the chains snap back to the original position. Natural rubber is an addition polymer that is obtained as a milky white fluid known as latex from a tropical rubber tree. It is from the monomer isoprene, 2-methyl-1,3-butadiene. Since isoprene has two double bonds, it still retains one of them after the polymerization reaction. Natural rubber has the cis configuration for the methyl groups. Vulcanization of rubber. Charles Goodyear accidentally discovered that by mixing sulfur and rubber, the properties of the rubber improved dramatically. It now became tougher, resistant to heat and cold, and also possessed increased elasticity. This process was later called vulcanization, after the Roman god of fire, Vulcan. The development of vulcanized rubber for automobile tires greatly aided this industry. The process consists of heating a mixture of raw rubber with sulfur and an appropriate additive at a temperature range between 373 Kelvin to 415 Kelvin. This causes shorter chains to cross-link through sulfur to longer chains. More specifically, sulfur forms cross-links at the reactive sites of double bonds, and thus the rubber gets stiffened.